Decode Ways. Imagine this: you're in a high-pressure tech interview, and you're handed one of the trickiest DP string problems out there, Decode Ways. This Pattern Mastery 100 staple isn't just a test of coding, but of true problem breakdown and logic. Did you know that over 40% of candidates get tripped up by edge cases with leading zeros or multi-digit decodings? If you can master Decode Ways, you'll be ready for any string or DP problem thrown your way. So let's crack it together. Here's the breakdown. You're given a string of digits, like 102,213, and each digit or pair of digits can map to a letter, 1 to A, 2 to B, 26 to Z. Your job? Count how many ways you can decode the string, following those rules. A 0 on its own is invalid, but 10 is valid since it maps to J. What are all the possible decoding paths? Now, let's assess the challenge. A brute force recursion would explore every way to split the string, but it's way too slow. We need dynamic programming. For each position in the string, we'll store how many ways we can decode up to there. Key edge cases? Zeros. 0 isn't a letter, but 10 is valid. We need to handle both single-digit and two-digit decodings. Here's how we'll structure it. Set up a DP array where dpi is the number of ways to decode the first I characters. Initialize dp0 equals 1, empty string is one way. For each position I from 1 to n. If si1 is valid, not 0, add dpi1. If si2:i is between 10 and 26, add dpi2. Solution 1. Recursion with memoization time complexity. ON. We begin by defining a class called solution. This is just a neat container for our decoding method. This defines our function numDecodings, which computes how many different ways we can decode a digit string into letters. Remember, 1A, 2B, 26Z. We store the length of the string in n. This lets us know when we've reached the end during recursion. We create a dictionary called memo, which will store results for already visited positions. Memoization helps us avoid recomputing, giving us a time complexity of ON. We define a recursive helper function called DFS, which tells us how many valid decodings exist starting from index I. This checks if we've reached the end of the string. If so, that means the entire path leading here was valid. So we return 1, representing one valid decoding path. If the current character is 0, it cannot be decoded by itself. There is no letter that maps to 0, so we return 0, meaning no valid decoding from this point. If we're at the last character and it's not 0, it must be valid by itself. So there is exactly one way to decode that last character. Thus, we return 1. We check whether we've already computed the number of decodings starting from index I. If we have, we can reuse that answer immediately. So if the memo contains it, we return the saved value, instant lookup. We initialize our result by first decoding one character. This represents the scenario where we treat SI as a single-digit letter. We now check whether the next two digits form a valid letter, from 10 to 26. If so, there is another decoding option available. Decode two digits together. If the two-digit number is valid, we add the number of ways to decode the rest of the string starting from I plus 2. This is like branching the decision tree. One branch for single-digit decoding. One branch for double-digit decoding. We store the result for index I in memo so future calls don't repeat the work. We return the total number of decoding paths starting from index I. Finally, we start the entire decoding process from index 0, the beginning of the string. Final wrap-up. And that's how this algorithm works. It first sets up memoization and a recursive helper, then explores both single-digit and double-digit decoding options while saving results to avoid repeated work. Efficient, simple, and elegant. Test case check. Decode ways using recursion plus memo. Let's test our function using this input. 12. This string represents an encoded message where each digit or pair of digits maps to a letter. 1A, 2B, 26Z. Here's why the solution works. We use recursion to explore every valid way to decode the string. First, we try decoding one digit at a time. Then, if the next two digits form a valid number between 1 and 26, we explore decoding them as a pair as well. Memoization ensures we don't recompute results for the same index more than once. And that's exactly what our program outputs, too. This confirms that the recursive plus memoized approach is working correctly and matches the expected result. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths by exploring single-digit and double-digit options, efficient, accurate, and reliable. Solution 2. Bottom-up DP time complexity. ON. We begin by defining a class called solution, which simply groups our decoding method neatly. This is our main decoding function. It tells us how many ways we can convert a digit string into letters, where 1a, 2b, 26z. We store the length of the string in n so we can build our DP table. We check whether the input is empty. No digits means no decodings. So for an empty string, the answer is simply 0. We create a DP array of size n plus 1, all initialized to 0. Each DPI will represent the number of ways to decode the substring starting at position I. This array gives us our bottom-up dynamic programming structure. We set the base case, dpn equals 1 means that when we reach the end of the string, there is exactly one valid way to decode, by doing nothing. This is a common trick in DP for decoding problems. Now we set the value for the last real character. If the last character is 0, it cannot be decoded, so dpn 1 equals 0. Otherwise, it's valid as a single letter, so dpn 1 equals 1. We now fill the DP table backwards, from right to left. Each index I represents a subproblem. How many ways to decode starting at position I? This loop runs n times on. If the current character is 0, it cannot be decoded on its own, so dpi must be 0. Thus, there are 0 ways to decode starting from index I if si is 0. If the digit is not 0, it can be decoded as a single letter mapping. So first, we count the ways to decode by treating si as a single digit letter. That's why we copy dpi plus 1. This represents the one-step decoding path. Now we check whether the next two digits form a valid letter between 10 and 26. If they do, we have a second decoding option. Decode two digits together. If the two-digit number is valid, we add the number of ways to decode the substring starting at I plus 2. This adds in the two-step decoding path. Finally, dp0 contains the answer for the entire string, the total number of ways to decode from the beginning. Final wrap-up. And that's how this algorithm works. It first builds a DP table from right to left, starting with simple base cases, then adds the number of one-digit and two-digit decoding paths for each position. Efficient, simple, and elegant. Test case check. Decode ways using bottom-up dynamic programming. Let's test our function using this input, 226. This string represents an encoded message, where each digit or pair of digits corresponds to a letter from 1a through 26z. Here's why the solution works. We fill a DP array from right to left, where dpi represents the number of ways to decode the substring starting at index I. If the current digit is 0, it contributes 0 decodings. Otherwise, we add dpi plus 1, decoding the current digit alone, dpi plus 2, decoding the current two digits together if they form a number less than or equal to 26. And that's exactly what our program outputs. 3. This confirms that our bottom-up DP approach is computing the decoding count correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths using an efficient DP table, reliable, accurate, and performant. Decode ways. Let's do a recap. So, how do you turn a string of numbers into letters, and how many ways can you do it? Decode ways is one of those deceptively simple dynamic programming problems that really tests your logic under pressure. Once you understand its structure, though, it becomes one of the most elegant DP challenges out there. Breakdown recap. We started by understanding the core problem. Given a string of digits, each single or double-digit number can represent a letter from A to Z. The goal is to count how many valid ways you can decode the entire string. But there's a catch: zeros can't stand alone, which makes handling combinations like 10 or 20 critical to getting the logic right. Assess recap. We compared the brute force recursion with dynamic programming. Recursion explores every possible split but grows exponentially. DP, on the other hand, builds the solution step by step by remembering how many ways we can decode each prefix. That's the key to handling overlapping subproblems efficiently. Structure recap. Our plan was clear. We used a DP array where each position represents the number of ways to decode up to that point. For each digit, if it's valid, not 0, we carry forward previous counts. If the last two digits form a valid pair between 10 and 26, we add in the count from 2 steps back. By the end, the final value tells us the total decoding count. Implement recap. We implemented this logic in Python and ran it on LeetCode without any errors. The DP solution worked efficiently in ON time and space, and we even noted that it could be optimized to O1 by using just 2 variables. Check recap. After running our test cases, the output matched perfectly with expectations. The DP table captured every valid decoding path, confirming that the logic worked for both regular digits and tricky zero cases. Closing insight. The big takeaway? Decode Ways teaches the heart of dynamic programming, breaking big problems into smaller overlapping parts. Once you master that pattern, you'll recognize it everywhere, from strings to sequences to any problem that builds on past results.